Hello and welcome back to Calculus 1, section 8.8 on 8th grade math, numerical integration. Yes, this section, all we're going to do is...
Calc 2.
Yeah.
What did I say?
Calc 1.
Calc 1.
This sounds like a...
Hello and welcome back to Calculus 2. This is section 8.8, which is 8th grade math on numerical integration. Why is this 8th grade math? Because the only thing you are going to do here is multiply and add numbers. So we are going to approximate area under the curve. This is used for definite integrals, right? Because we are looking for area under the curve, and that's definite integrals. And that in your later studies is going to translate into whatever application, right, you're using it for. So we are going back to Calc 1, just to remember one picture, one that we had was like this, and then we divided this into rectangles, and then we said, let's use left-hand sums. So we created these rectangles like this, whatever, and they don't have to be equally spaced, but it's cool if they are. This is your x0, x1, x2, x3, x4, and this is your a and this is your b, because this f of x function is exact area is given as integral from a to b of f of x dx, and this is your Calc 1. Now, what we claim is, since you have over here, you have 4 of these rectangles, right? When you look at this, observe that we are taking the left sums, meaning that you will be computing your function height on the left side of the rectangle, because that's the one that cuts through the function. So the first rectangle, area of the first rectangle, is going to be your delta x, right? And delta x is simply xn plus 1 minus xn, right? So x1 minus x0, x2 minus x1, x3 minus x2. So the next minus the previous, right? It will be the function computed at x0 times delta x. Area at 2 is function computed at x1 times delta x. Area for the third rectangle is function computed at x2 times delta x. And finally, area on the fourth one is function. So this is all review from Calc 1, right? All of these are Calc 1 review. And I have extra space over here, so it bothers me. Give me a second. Take that. Perfect. It's called what? CDO. Put their letters in a proper order. Alphabetical. All right. Okay, good. So now, what is the area? The area is approximately equal to the sum of all of these areas, so I'll call him AI, right? And that's simply going to be delta x times, and now you have your f of x0 plus f of x1 plus f of x2 plus f of x3, and you're done. So what do we have? We have addition of some numbers times delta x in front. So did I promise 8th grade math? I deliver, right? You need to know PEMDAS. Ooh. So this I is the counter. Counter that goes 0, 1, 2, 3, 4. Just tells you the location where you are, right? And you just go through and compute. You also have the right sums, so you can go and you can just draw the right sums going right from the right point. And in some cases, you make error above the line. In some cases, make error below the line, depending on what you want, the right sum or left sum, or whatever. And this is what you learned in Calc 1. So what Calc 2 has to offer? Calc 2 has to offer better methods, the ones that will have less error. Observe that if I am to take now red and color the amount of error that we get as we are using the left-hand sum, right? Well, all of this area here is error, and that's a lot of error, right? If you compare to how much actual area, let me just get rid of these blue ones. If you compare to how much area you actually have under the curve in this particular picture, this is a lot of error. So is there a way to make this better? And the answer is clearly yes. And those are going to. So we are going to go midpoint, then upgrade to trapezoid, upgrade to Simpson. If you take the courses later on numerical analysis, you will learn about cubic splines. You can actually go as high as you want in terms of the exponents. It's just at one point it becomes more hassle to compute, right, than the benefits of having, the precise answer. So, you will juggle that to figure out which one to use when you start using it for what it's supposed to be used for. So midpoint. So I'm just going to draw one of these. I'm going to draw something and erase it. Now, let me zoom in. Observe this, guys. If I use the left-hand point and draw the rectangle, all of this over here is error. And that's a lot of error. If I decide to use the right hand, then I get to draw right from this point here, and then I will be calculating the area of this, and all of this is error. So now I will undershoot, right, the actual area. So that's, again, a lot of error in here. So is there something that would be better? Well, if I go in the middle, and I create a rectangle here, observe that this particular new rectangle overshoots with area on one side but undershoots on the other. They don't cancel each other, but it's much better than having all of your error concentrated here or all of your error concentrated below, right? A lot of error gets canceled. So midpoint is absolutely superior if you are going to approximate the curve with these flat lines like this, right? The constants. So we learned the midpoint rule, and we clearly see why it's called a midpoint, right? Because it's in the middle of the interval. So if this is your xn, and this is your xn plus 1, which is the next point. So let's say 3 and 4, or 5 and 6, right? You will be still having your delta x to be x to the n plus 1 minus x to the n, xn. And now you will be calculating the function at the average of these 2 points, because it's in the middle. And that's xn plus 1 divided by 2. And that's where the middle comes in. So now, what's the formula? Well, the formula, remember, you are starting with x0. You are going to end up with xn at the end. And along the way, you have delta x as a spacing in between. So the area calculated using the midpoint is going to be equal to delta x times, and now you have f of x0 plus x1 over 2 plus f calculated at x1 plus x2 over 2 plus f calculated at x2 plus x3 over 2 plus dot 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 going all the way to function computed at xn minus 1 plus xn as the last one divided by 2, and you're done. So this is your formula for calculating. Delta x, let me write it here in blood. Delta x is always b minus a over the number of rectangles you get. You choose the number of rectangles. You want a 5, you want 7, or 8, or maybe you like pain. 28 rectangles, right? And you just compute that.
How many would be precise enough to be very close to the actual number?
Well, that depends on the type of the function. That is the function rising too quickly, rising right, or drop too quickly, or so it depends on the function. It's a fluent answer for that one.
How do you think we should use a limit to infinity when not do something as
Because you need to make this 0. And we are working with definite with a and b limits. So let's use this midpoint. Say that n is equal to 6, that the integral that we want to solve is from, let's say, should I make this annoying? No. 1 to 7. Of what? Whatever. Square root of x, who cares? Dx. Alright, so we draw our square root. We start at 1, 2, 3, 4, 5, 6, and 7. So we are interested in this area here. Now let's say that for some reason we are not able to integrate square root of x. So in that case, we partition this, and then we can use the midpoint to try and figure out this area. So now what I have is every midpoint is going to give a rise there we go. There they are. They connect down, obviously. So my delta x calculation is 7 minus 1 over 6, which is 6 over 6, which is 1. So delta x equals 1. So area is approximated with the area of the midpoint, which is given by delta x, which is 1, times function computed at, well, each midpoint. Now my midpoints are easy. 1.5, 2.5, 3.5. So I need to have 6 rectangles, because 6 rectangles, right? So I go and I say f of 1.5 plus f of 2.5 plus f of, right? These are all the midpoints, guys, right? 4.5, 5.5, and then plus f of 6.5, and what this means is simply square root of 1.5 plus square root of 2.5 plus square root of 3.5 and all the way to 6.5. Now you take your abacus and get the decimals over here, right? So what do we get as we compute all of these? $11.69. Okay. Now, let's calculate the integral because we can. Square root of x 1 to 7 dx. We know that integration for root x is going to be x to the 3/2 over 3/2 computed from 1 to 7. So we have 2/3 times 7 to the 3/2 minus 1 to the 3/2 is just 1. So what do we get here? Seven raised to the 3/2 minus 1 times 2/3 times 2 divided by 3, 11.68. You see how good the midpoint is? Right? So why is the midpoint so good? It's so good because when you get that line in the middle and you draw the horizontal for the rectangle, some of that overshoots as an error, some undershoots, and they roughly cancel out, leaving some difference in as an error. So midpoint is awesome. Can we do better? Yes, we can do better. Right? So this is where we get the trapezoid rule. If you're not familiar with geometry, here we go. This is a trapezoid. Trapezoid has the set of parallel sides, and those sides are called A and B, shorter and longer base. You do still have a height of the trapezoid, so this would be the height of the trapezoid. And unfortunately, we never care about those sides. Trapezoid could be a right trapezoid if it looks like this. You have 90-degree angle on this side, and you still have your A. Hold on, come on. A and B, and you still have the height. Now the height is this side, and so on. What is the area of the trapezoid? Does anyone know that? Very good. It's A plus B over 2 times the height. Who had his hand? Yeah, that's why I said very good. Now, time to draw a function. If I partition this, let's say every 2 squares like this, and then stop, look what I can do. I can connect these points with a straight line. The first one is a triangle, clearly. But look at this one now. This one is this one flipped on the side, right? If you stand it up on edge, you get the one over there. So what's the role of edge? The role of edge is delta x, right? Do we all see that? Stare at it until you figure out that edge is the delta x. So now I have delta x's everywhere over here. And what are my A and B? These guys are my A and B. So if I want to find, so now I label this x0, x1, x2, x3, x to the 4, let's say x to the 5, and then we stop. If I, let's say, pick rectangle number, trapezoid number 3. Trapezoid number 3 looks like this. That's the trapezoid number 3. And this is my x2, this is my x3, and this is my delta x. I know that it passes through function in these corners. So wouldn't the area of this be given by function computed at x2 plus function computed at x3 divided by 2 times delta x? This is your A, this is your B, this is your H. I'm going to change the color. This is, well, A and B are switched here. This is your B, this is your A, and this is your H, and this is F. The way I drew it up there, you see that A is the longer side, so that's why I use x cubed. You can have different function and they will be switched, whatever. So when I want to calculate this, I say, well, first of all, do you see that this side is shared between rectangles 2 and 3? And we calculated twice, right? Good. Which explains the pattern that we have for trapezoid rule. The pattern for trapezoid rule, area trapezoid, is going to be delta x over 2, and now I have f of x0, that's the first value. This x0 is always, by the way, your a in the integral. And then you have plus 2 f of x1 plus 2 f of x2 plus 2 f of x3 plus dot 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 plus 2 f of xn minus 1, and finally plus f of xn, the last term, that's, by the way, your b. So note the pattern. The coefficients inside this bracket is 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 1 at the end. So we can use trapezoid rule now to find an area under a curve. So which problem should we do? Let's see if they have a problem in the homework, let's say. A hot air balloon is launched from an elevation of 5,400 feet above sea level. As it rises, the vertical velocity is computed using a device called a variometer that measures the change in atmospheric pressure. The vertical velocities at the selected times are shown in the table. Great. So now we have a table, and T in minutes and velocity in feet per minute. So we start with a 0, then we have 1 and 100, then we have 1.5 and 120, then we have 3 and 150, then we have 3.5 and 110. Then we have 4 and 90 and 5. So what do we see about a velocity from this data for this balloon? What can we tell by the data over here? We see that the time, as the time progresses, what's happening with velocity? It decreases. Velocity decreases. All right, so
it increases then it decreases.
Yeah.
It's one phase down. The maximum.
It goes 0, 100, 120, then 110, 90, 80, right? So that's something like that. We don't know it's a parabola, but it's okay. All right, so what do? Well, we use trapezoid rule. Now, note that the increments here are from 0 to 1 is 1, and then from 1 to 1.5 is 0.5, and then from 1.5 to 3 is, you do not have to have all of this perfect, right? Now, this would be the height of your function, and this would be the x value on the, right? So, what do? First off, we don't get to use overall delta x here because they're different, right, as you jump from one to another. So what we're going to do instead is we're going to calculate each one of these separately, right? Here is my number 1. That's my number 1. And then here is number 2. And then number 3. And so on. Because these are your values that you are using at the edge. So now if I want to graph this, I use 1, and then 1.5, 2, 3, 3.5, 4, and then 5. So these are the times. The velocity over here, right on top, goes this way. So now what do? Well, we don't actually need the heights. We can just use these ones. So you do not have delta x in this case because it's not evenly spaced. So our area of the single trapezoid is going to be what? We said x0 plus x1 over 2. Sorry. No, I was right. x0 plus x1 over 2 times the delta x. But that's each delta x over here is going to be different when you go from rectangle to rectangle. So what do I have? I have at 0 is 0, at x1 is 1, divided by 2 times the difference is, oh no, it's 0 and 100, sorry, 100. So we get 50 for the first area. Then area, I meant to say area 1. Area 2 is going to be x1 plus x2 over 2 delta x. So x1 is 100, and then plus 120 divided by 2 and times, now you have a 1/2 in here. So this is 220, 110, 55. A3, x2 plus x3 divided by 2 times delta x. So x3 is 120, no, I lied. x0, x1, x2, x3 is 150. So 150 plus 120 divided by 2 times the separation is 1.5, so we can call that 3/2. This is 170, 270 times 3 over 4. So that's 600, 810 over 4, 810 over 4. And when you cancel that by 2, cancel it by 4. I'm sorry? 2.5. Can you just go in this fashion? Calculate all of them, all the way A2, A6. Because we have 1, 2, 3, 4, 5, 6. We have 6 rectangles. So you will go all the way from A1 to A6. There is one more rule called Simpsons Rule. But I guess you want to go.
Yeah, it's 7.5.
Bye. Oops.